Hello, I am Krishna Shetty and I'll be presenting on the research paper titled GANs for Medical Image Synthesis and Empirical Study. As the title suggests, the paper discusses the use of generative adversarial networks, GANs for short, in medical imaging. A brief TLDR version of the paper and its conclusions can be summarized as follows. The authors performed a study to evaluate the effectiveness of GANs in generating medical data and tested various GAN architectures on 3 different medical imaging modalities: cardiac sign, MRI, liver CT, and RGB retina images. They found that some GANs were better suited for medical imaging applications than others, and that the top performing GANs were able to generate realistic looking medical images. However, segmentation results suggest no GAN was able to reproduce the full richness of medical datasets. Before delving into understanding the paper and the inferences that it draws, let's briefly go over what GANs actually are. GANs primarily follow an unsupervised approach to machine learning. Generative adversarial networks, that is GANs, are a type of machine learning algorithm that is made up of 2 parts, a generative model and a discriminative model. The generative model is trained to generate new data such as images that are similar to the training data. The discriminative model is trained to distinguish between real data and fake data generated by the generative model. The 2 models are trained together in competition, with the generative model trying to fool the discriminative model and the discriminative model trying to correctly identify fake data. Through this competition, the generative model learns to produce more realistic data, while the discriminative model becomes better at identifying fake data. GANs have been used to generate a wide range of data, including images, audios, and texts. GANs are usually used to increase dataset size by producing artificially entries. The figure shows the overall structure of a GAN. The paper also briefly mentions most widely documented learning problems suffered by GANs, which happen to be convergence, vanishing gradients, and mode collapse. Conversion occurs when generator becomes too powerful and learns to fool the discriminator with a faulty output. And in case of the discriminators randomly guess the output, thus achieving an accuracy of 50% and not helping the generator to learn. GANs can struggle because the training process involves 2 networks pushing against each other without a clear winner. Vanishing gradients is a common problem in deep learning in general. Vanishing gradients can occur when the discriminator outperforms the generator, causing the loss to go to 0 and the gradient to become small, which hinders the generator's ability to learn. Mode collapse occurs when the generator only produces a handful of outputs instead of covering the diversity of the entire dataset. These challenges can make it difficult to train effective GANs. The figure shows samples generated by 2 different GANs. Row 1 has all 10 modes, i.e. all characters from 1 to 9, whereas row 2 has only 1 mode, for 6. This is mode collapse, a form of GAN failure. The GANs that the paper will test are DC GAN, that is deep convolutional GANs, LS GAN, that is least square GANs, W GAN, that is Wasserstein GANs, and W GAN GP, that is Wasserstein GAN with a gradient penalty, Hinge GAN. It will also cover SPADE GAN, that is spatially adaptive denormalization, and Style GAN, style-based GAN, which happen to be state of the art. The GANs were trained on 3 datasets: IDRID, SLiver07, and ACDC datasets, with training size increasing in that order. Figure 3 shows examples of images and the segmented structures for ACDC, SLiver07, and IDRID datasets, while figure 4 is a summary of the style GAN generator model architecture. The metrics used are FID, i.e. the Frischer inception distance. The metric has a lot of shortcomings mentioned in detail in the paper. However, it is the best metric available to measure GAN's conformity right now. They use another GAN downstream based on the UNet architecture for the segmentation task, which is trained on the data created by the first GAN. This achieves in measuring the actual effectiveness of GANs, as GAN data happen to be used by other GANs or models downstream in real-world applications. Figure 5 is the equation for the Frischer inception distance, while figure 6 is the UNet architecture. Experiments and results. Figure 5 shows examples of generated images for each GAN on the AC/DC, S-Liver07 and IDRID datasets. The first column is an example of image from the real dataset. As the images tell, Spade and Style GAN produced impressively photorealistic results, which were good enough to fool trained medical professionals with 15 plus years experience 40% of the time. Here are the results in a tabular form. The lower the FID score and the higher the unit dice score, the better. This table reveals that FID score and unit score do not necessarily express the same thing. The FID score might be a good proxy to distinguish the best methods from the least effective ones, but it does not correlate well with an application score such as DICE. For example, the FID score of 29.06 of Style GAN on S-Liver07 suggests that the produced images are much more accurate than those of Spade GAN, with an FID score of 47.62. However, as you can see, the resulting DICE scores show that Spade GAN is significantly better than any other model. A similar comment can be made on the IDRID and AC/DC, as Style GAN and Spade GAN got similar DICE score but very different FIDs. As for the FID score of 1.09 obtained by Spade GAN, the associated 82% DICE score suggests that the network has most likely memorized the training set. This might be attributed to the small size of the IDRID dataset as well as the simple shape of the input segmentation mask. Thus, a key thing that the paper discusses is the use of Frechet inception distance score as a metric for evaluating the effectiveness of generative adversarial networks in medical imaging. The authors plotted the inception net latent space of the generated images obtained with the most and least effective GANs and found that the distributions were similar for both GANs. However, when they plotted the unit latent space for the same images and GANs, they found that the distribution were more distinctive, with the unit distributions of most effective GAN, that is the Style GAN, showing more similarity to the original dataset. This suggests that the FID score may not be a reliable medical imaging metric, as it is based on non-medical dataset, that is the ImageNet dataset, and its use in medical imaging should be made with caution. Conclusion. The paper discusses the use of generative adversarial networks, that is GANs, for medical image synthesis and presents the results of an experimental study on 3 different datasets. The authors found that GANs are not always effective as a source of medical imaging data, even if the generated images are nearly indistinguishable from real data. They also found that traditional metrics used to evaluate GANs are less robust than task-based evaluations. Overall, the study suggests that more research is needed to develop better generative models for medical data that take into account the specific nuances of this type of data. Thank you.